Okay. So dear students, in last class we have discussed about indefinite integration. Okay, we covered almost all topics and we solved some problems on indefinite integration. Okay, now coming to the definite integrals. So indefinite, definite. So that means here the integration is defined in a particular bounds, that is you have lower and upper bounds here. So indefinite integration, just we write like this: integral x square dx, find integral x square dx. But coming to the definite, so here you have to define where you have to find this integration. Okay na? So for example, integration from a to b. So this is lower and this is upper, lower bound and upper bound. So that means if you know very well indefinite integration, then definite integrals are very easy. Okay now? Here we cover the topics: fundamental theorem of integral calculus and geometrical representation of definite integrals and properties of definite integrals, reduction formula, at last application of definite integrals, which are finding the areas under the curve. So this is the application of definite integrals. Okay now, so we covered this concept in this chapter. Okay now? Okay, so first we will discuss fundamental theorem of integral calculus. Okay now? So what is fundamental theorem of integral calculus? In first year we discussed fundamental theorem of differential calculus. Okay now? Here, so let f is mapping from closed interval a comma b to r is a integrable function. Is a integrable function. Integrable function. And if there exists capital F mapping from closed interval a comma b to r. See, every function goes to r, real number. That means these functions are real valued functions. We are discussing this calculus in real valued functions only. Okay. If there exists capital F from closed interval a comma b to r, which is a differentiable function. Differentiable function such that capital F dash of x equal to f of x. Capital F dash x equal to small f of x. Okay now? So what we have to take? If f is mapping from closed interval a comma b to r is an integrable function, and if capital F from closed interval a comma b to r is a differentiable function such that f dash x equal to f of x, f dash x equal to f of x, then integral a to b f of x dx equal to capital F of b minus capital F of a. Okay, so this is the fundamental theorem of integral calculus. Okay, clear? Small f is integral function, capital F is differentiable function, such a way f dash equal to f. Okay, then integral a to b f of x dx equal to f of b minus f of a. Here this a is lower limit. This a is lower limit. This b is upper limit. This b is upper limit. So as usual, this f is integrand. Okay, this f is integrand. X is variable. Okay, so this is is the fundamental theorem of integral calculus. Clear? Okay, so now we will give one example. So find the integral 1 to 3. Okay, find the integral 1 to 3 x square dx. Okay, find the integral 1 to 3 x square dx. Okay, now what is the integral x square? In indefinite integration, we learn the integral x square, which is of the form x power n. So this is equal to x cube by 3. Okay, na? So from 1 to 3. So this is lower limit, this is upper limit. So this is equal to 3 cube by 3 minus 1 cube by 3. Okay, you have to substitute upper limit as well as lower limit in place of x. Now this is equal to, so 3 square 9 minus 1 by 3. Okay, na? So this is, so 27 minus 1, 26 by 3. Okay, na? That's all. Okay. So now we discussed fundamental theorem of integral calculus. So which is integral a to b f of x dx equal to f of b minus f of a. So actually what is the geometrical interpretation of this definite integral? What it means of definite integrals? Okay. So actually finding the definite integration, suppose finding the definite integral of, for example, a to b f of x dx means we are going to find the area under this curve, within the limit of x axis and ordinates x equal to a and x equal to b. Okay, na? Suppose this is y equal to f of x. Okay, na? X axis, because here variable is x. Suppose if variable is y, you have to consider y axis. Okay, you have to consider y axis. Now the limits are a to b, that means the limits x equal to a to x equal to b. The meaning of integral a to b f of x dx means here these limits are x equal to a, x equal to b. So x equal to a, what is this? This is the ordinate, y coordinate. Okay, ordinate, these are the ordinates, these are the x values, these are the y values. Okay, na? Fine. So the real meaning of definite integration is finding the area under the curve within the limits. Okay, na? So we will explain more how it represents. Okay. See, now we have to find the area under this curve between these red lines x equal to a and x equal to b and this x axis. Okay, see, observe all these parts. See, actually I divide this this interval a to b interval, some parts, for example n parts here up to xn. Okay, now some parts. Now each part denotes one rectangle. Yes or no? Each part denotes one rectangle. Actually these are the trapezium. See, one rectangle and triangle. So this is the trapezium. So now first of all eliminate these small parts. These are the error parts. Eliminate this. So what are these? These are the rectangles. These are the rectangles. So what is the area? What is the area? So area equal to, so let it be, area of this one is A1. Area of this one is A1. A1. This is A2. So on, this is AN. Okay, na? Now A equal to, total area equal to A1 plus A2 plus so on AN. Yes. Now what is is the area of this one? See, delta xi, that is the length, the difference of this. That means this length is xi minus 1 in particular rectangle. Okay na? So this is x1 minus x0. This one x2 minus x1. Each are equal. So this length is in general delta xi. So this one is delta x1, and what is this? This is the value of y equal to f of x na. So this is the value of f of xi. I mean in general this is f of xi. So this is equal to, what is this? F of x1 star. Why I am using star means this one is you can take anywhere, here, anywhere. Okay na? Into delta x1. Area of the rectangle, length into breadth. Okay na? So this is the breadth, delta x1. This is the length, f of x1 star. Okay. Similarly, f of x2 star into delta x2 plus so on, plus f of xn star delta xn. So this is equal to summation from I equal to 1 to n f of xi star into delta xi. Understood? So the area of this one is summation of area of all these rectangles. But is it not exact area? It is the approximate area, because we exclude some small triangles areas. Those are small triangles areas. So you have to write here approximation. Okay na? Approximately equal to. Fine. Now, so if you divide this rectangles very small, suppose 1 to 10, if you make 10 parts, the length is 1. If you make 20 parts, the length is 0.5. If you make 100 parts, the length is 0.1. So if you make, these lengths are very small. I mean, again if you divide small rectangles, with small rectangles, then what will be happen? Then these errors will be excluded. That means if you make more intervals, if you make more partition, then these errors will be excluded. Okay na? So that means if n goes to infinity, that means the number of subintervals, okay, the number of partition goes to infinity, then what will be happen? These errors will be overcome. Okay na? So then what will be area? So in that case, the area A equal to limit n tends to infinity, summation I equal to 1 to n f of xi star into delta xi. Because limit n tends to infinity means the error will be overcome. So we are using equal. Okay na? So this becomes actually the area of this region. So this is equal to, this is nothing but integral a to b f of x dx. Integral a to b f of x dx equal to limit n tends to infinity, summation from I equal to 1 to n f of xi star into delta xi. So this is the meaning of the definite integration. Okay na? Here delta x is the length of the, here the partition, that is the length of the rectangle. Fine? Okay. Now from this we write some formulas. So those formulas are, you have to remember. In particular, that means here a to b na. In particular, integral 0 to 1 f of x dx equal to limit n tends to infinity 1 by n summation from I equal to 1 to n f of I by n. What I am doing here, this delta x, the length of the interval. What is the length of the interval? 1 by n, because the total will make n parts. So the length is 1 by n. So I take 1 by n outside. So this xi star is the value of this value is, suppose in this interval I by n, in this interval 1 by n, in this interval 2 by n, so on. Okay. So integral 0 to 1 f of x dx equal to limit n tends to infinity 1 by n summation from I equal to 1 to n f of I by n. So this form is called definitive integration in infinite limit form. Okay, finding the definite integration in infinite limit sum. Infinite limit sum. Okay, because n tends to infinity means this sum is infinite sum. Okay, suppose the limits are integral 0 to p f of x dx equal to limit n tends to infinity 1 by n summation from I equal to 1 to np f of I by n. Okay, so you must remember these formulas. You must remember this formula. Okay, understood? So if the limits are 0 to p, you have to use this one. If the limit is 0 to 1, you have to use this one. Fine. So finding the definite integration by using infinite limit sum, then you have to use this formula. Otherwise, by fundamental theorem of the integral calculus, which is f of b minus f of a, it's very easy. Okay, so I will give one example. Okay, so now we will give one example to find the definite integral by using the infinite limit sum. Okay, so the problem is find the integral of 0 to 2 x square plus 1 dx by using infinite limit sum. Okay, na? Okay, first of all we calculate this by using fundamental theorem of integral calculus. Okay, to verify the solution by using both the methods. Okay, na? So by using fundamental theorem of integral calculus, so what is the value of this one? Integral 0 to 2 x square plus 1 dx equal to, so x cube by 3 plus x cube by 3 plus x from 0 to 2. Okay, so this is equal to, so 2 cube 8 by 3 plus 2 minus, if you substitute 0 you will get 0, f of b minus f of a, fundamental theorem of integral calculus. So which equal to, so 3 2s are 6, 6 plus 8 14 by 3. So this is the integral value of this function by using fundamental theorem of integral calculus. Okay, so remember this value. Okay, now we do this problem by using infinite limit sum. Okay, so what is infinite limit sum? By using infinite limit sum, so integral 0 to 2, that means this is of the form integral 0 to p f of x dx equal to limit n tends to infinity 1 by n summation from I equal to 1 to np f of I by n, okay, limit n tends to infinity 1 by n, summation from I equal to 1 to np f of I by n. Okay, here I mean in this problem here what is p? P equal to 2. Here p equal to 2. So what is f of x? F of x equal to x square plus 1. Okay na? Now you have to substitute these values in infinite limit sum. Okay. So this equal to limit n tends to infinity, limit n tends to infinity 1 by n summation from I equal to np, p value 2, so 2p, sorry 2n, np, okay, 2n, f of I by n. So in place of x you have to substitute I by n, okay. So I by n whole square plus 1. Understood? Limit n tends to infinity 1 by n summation I equal 1 to np means 2n, f of I by n. So f of I by n means I by n whole square plus 1. Clear? Now this equal to, so limit n tends to infinity, okay, 1 by n. So apply the summation, what you will get? For I equal to 1 by n whole square plus 1 plus for I equal to 2 by n whole square plus 1 plus so on. What is the last term? The last term is for I equal to n, 2n by n whole square plus 1. Understood? Here don't try to cancel this n and n, okay, don't cancel it, okay. Now this equal to, so limit n tends to infinity 1 by n, okay. Now here 1 by n whole square plus 2 by n whole square plus so on plus 2n by n whole square plus how many n's are there? How many ones are there? 1, 1, 1. How many ones are there? The summation from I equal to 1 to 2n. So there are 2n ones are there. So that means we will get here 2n. Yes or no? 2n ones are there. So plus 2n. Understood? Now this equal to limit n tends to infinity 1 by n. So here up to here you can take common, that is n square as LCM. If you take n square as a LCM, the numerator 1 square plus 2 square plus up to 2n whole square plus 2n. Understood? This is here n square, here n square, here n square. So n square is the LCM. So numerator 1 square plus 2 square up to 2n whole square plus 2n. Okay. Now this is equal to limit n tends to infinity, limit n tends to infinity, okay. So 1 by n. Now what is this? See, what is this? Sum of the squares of the 2n terms. So that is n into n plus 1 into 2n plus 1 by 6. Okay. So that is n means 2n. N into, okay. So I will write here. So this is equal to, so limit n tends to infinity 1 by n. So what is the sum? Sum of the squares of the 2n terms. So n into 2n into n plus 1 2n plus n into n plus 1 into 2n plus 1. So 2n plus 1 means 2 into 2n, which is 4n. n into n plus 1 into 2n plus 1 by 6. So 6 into n square plus 2n. Okay, understood? This form is n into n plus 1 into 2n plus 1. Okay, 2n plus 1 by 6. So this is equal to limit n tends to infinity 1 by n. Now take here n and here common. So that is 2n cube into 2 plus 1 by n. Here 4 plus 1 by n by 6 n square plus 2n. Okay now? Now this is equal to limit n tends to infinity. So this is 2n cube into 2 plus 1 by n into 4 plus 1 by n by 6n cube plus 1 by n into 2n, which is 2. Now, so apply the limit here, cancel n cube. Here n cube will be cancelled and 2 1s are 2 3s are. So if you apply the limit n tends to infinity, this becomes 0, this becomes 0. So 2 into 4, 8 by 3 plus 2, which is equal to 14 by 3. Yeah, which is equal to the value of integration by using the fundamental theorem of integral calculus. Okay now?